Welcome to EPG Pathshala. This is a series of lectures in computer science. The subject we are looking at is computer networks. This is the second lecture that we have on computer networks. So, what we will be looking at in today's lecture would be a little bit of needs of the applications and some details about performance of a network. So, the objectives for this session would be as follows. We would try to understand the different demands that an application places on the network. So, we look at it from an application perspective, and then to understand how these different layers that we talked about, that we mentioned in the previous lecture, meet those demands, and also try to understand the performance parameters of a network. So, how is it, what are the different factors which would have to be considered to understand the performance of a network. So, a quick recap of what we had seen in the previous class, on the previous lecture. So, we talked about network edge, network core and access networks. Applications and hosts constitute the network edge, routers, network of routers is your network core, and we have different communication links, and then we talked about protocols. So, flow of data through the protocol stack, remember that the data will flow through each layer physically up to the physical layer and then through the physical links, okay, and everywhere it goes through the various layers before it reaches the other end. So, now coming to the requirements that we have for a network. So, that is we said that there are these 5 different layers that we have. We are trying to understand what exactly is the function that is required from each of these layers and why exactly we need these layers. So, to delve a little bit deeper into that, what we will do is we will first take a 2 node network. Okay. So, let us say I just have 2 nodes, right, that I want to connect up as a network. So, what is it that I will require to set up a communication for an application like file transfer? So, first thing I need is I need a cable to connect the 2 machines, right. So, that is the first thing that I need. So, I have my physical layer set up, right, I have machine A, machine B, I have a cable. So, is this enough? Obviously, the answer is no, we need something more. So, what do we need? Maybe something to say, you know, that okay, I am transferring data, or that you can transfer data. So, some kind of a handshake is required between the 2 machines. So, you may have some signal, like for instance maybe a request to send signal, and your machine B may say yes, you can send the signal. So, it says it is clear to send signal. So, some signals which are required between the 2 machines to allow this data transfer to take place. So, is this enough? Again, if you ask, you will find that again that is not enough. You will need some kind of an agreed upon syntax for the data. So, the 2 sides should agree on how the data will be sent. They will be sending it as blocks of data or 1 byte at a time. Okay. So, we need to agree on some of these aspects. Okay. So, would that be enough? Not, again, that is not enough. So, what do we need further? There could be other things, like there could be something like some kind of a disturbance or interference effects which could affect the transmission. So, there could be errors which occur when you are doing the transmission. So, if an error occurs, what do? You will have to detect the errors, and you will have to either retransmit or ask for some correction, something has to be done. So, we will need some kind of error detection and error correction mechanisms, right. So, this is something that we will have to do. So, in addition to this, is there anything else that we would need? The answer is yes, we will have to do something called flow control, which is controlling the flow. What do we mean by controlling the flow? You could have your transmitter and the receiver working at different speeds. I can have a very fast transmitter, but a very slow receiver. So, what would happen then if the transmitter was transmitting data at its own pace? The receiver would not be able to receive all the data. Okay. So, what we need is we need to have some kind of mechanism to synchronize them. So, the flow of data should be controlled by the receiver. Okay. So, that a fast sender should not overwhelm a slow receiver. So, we need something called flow control, right. So, you see that there are, in addition to that physical wire that we had, we need certain other functionalities even for a simple 2 machine network to work. Okay. So, if you sum up the requirements for a 2 node network, you can see that we need a physical media obviously, and then we need some kind of a protocol which will allow for handshaking, which will specify the format for the data, which will do error control, flow control, synchronization and so on. Okay. So, this physical media, whatever we had, and converting it from data into signals and sending out is normally taken care by the physical layer, and these functions of putting data into a frame, doing error control, flow control are all handled by the data link layer. So, data link layer functions we say therefore are handshaking, formatting of data, framing, error control, flow control and so on. So, now this was our simple 2 node network running just one single application. Now, let us just add a little more from the application side. Suppose we want to add more applications. Okay. So, we talked just about a simple file transfer. So, let us say we want to also have a chat application between the 2 nodes. So, what do I need in that case? I will need a function which is able to distinguish as to whether the data is coming from the chat application or the file transfer application. on the sender side, and on the receiver side again do the same distinctions so that it is able to deliver the data to the correct application. Okay. So, we say that we need a function which can multiplex or demultiplex between the applications access to the network. That is, the applications are accessing a single network, single resource that you have. So, that access to that resource has to be controlled by some layer which is sitting in between, or a function which is sitting in between. That is our transport layer. So, it is the one which provides the multiplexing demultiplexing function, so that it allows multiple applications to access the common network which is available. So, if you look at the layers that we have in this 2 node network, you can see that the functions that we looked at just now can be looked at like this. So, we had the physical layer connecting up with the connected up by means of the physical wire. Then we have the data link. Okay. So, you have a logical connection between these two. Then we have a transport, again a logical connection between these two, and then multiple applications which could be running, which are talking to each other. Okay. This is our 2 node network model. Now, let us expand this to a larger network. Let us add more nodes to the network. So, what do we need to do now? First thing we need to figure out is how to connect the nodes in the network. So, if we talk about connecting the nodes in the network, one thing we talk about is something called a topology. That is, what is the structure that we use to connect up these networks? It could be a star topology, a ring topology, a bus topology, and so on. Okay. Now, when you have multiple nodes connected to some kind of a shared medium, we also need to know how they will access this medium and how they will share this medium. For instance, when the medium is shared, obviously two people cannot be transmitting data at the same time. So, then you will need to know who will get access to the medium, who will be able to transmit the data. So, we need something called media access. Okay. And when there are multiple nodes, obviously we need to have a mechanism to identify the node that we need to talk to, right, because if there are multiple nodes, then who am I actually talking to? So, I need addresses. Okay. So, you need addresses, you need some kind of a media access, we need to have a topology that will use that you will decide upon to decide on how these things are going to be connected. So, all these things you can say come under the purview of media access sublayer. Now, the media access we call it as a sublayer because it is something which comes as part of the data link layer or layer 2 as we call it. So, the different topologies that you must be familiar with are these 3: ring, star and bus. So, bus you have a single bus to which multiple devices are connected. Ring, they are connected in the form of a ring. In the case of a star, you have a central hub or a switch using which different devices can be connected. Of course, each of them have their own advantages and disadvantages, but the one that has really stood the test of time is the star topology with a centralized switch. The switches are getting more and more sophisticated, so which makes the star topology as one that is more and more commonly used. So, what happens when the network becomes even bigger? That is, we are not looking just as a small local area network, but we are looking at an interconnection of different networks through routers and through various links. So, in this case what would happen is that I would need to add one more function. What is that one more function that you will need to add? Now, since you have multiple devices, multiple routers through which the networks are connected, you need to have a path, you need to find a path through the routers to reach the destination from a source. Since there may be multiple paths available, so you need to choose one of the at least one as the path that you will use to go from any source to any destination. Okay. So, which is called as the routing function. And once you found that path, you keep track of that path, and when the data actually comes along, you must be able to send it along that particular path, right. So, that is another functionality that we have at this for this particular interconnection to work. Another thing that could happen is when you have multiple networks connected up together, one of the problems you could end up in is congestion. That is, you have too much of data coming into the routers, into the network, but the routers are not able to handle the amount of data that is coming in. Okay. So, that would lead to congestion, right. So, all these functions, handling of all these functions can be grouped together into another layer, which is called as the network layer. Of course, there is one more that you will need to add normally at the network layer, which is some kind of a network or a global addressing mechanism, so that you are able to do this routing function in an efficient manner. So, with this we end up with what we call as the 5-layer model, right. So, starting from just a 2 node network, if you keep on adding complexity to the current situation that we have today, which is a network of networks or a global network that we have today, the internet, you can see that there are at least these 5 different layers that we have. So, this is what has given rise to our 5-layer TCP IP model. So, we have the application layer, the transport layer, the network layer, then the link plus MAC, the media access control layer, and the physical layer. So, with this 5-layer model, you can see how the data will flow in terms of the protocols at these layers, okay, from one end to another end. Okay. So, let us take a simple example of a HTTP protocol in use, that is we are talking about a web browser. So, you have a web client, a browser here, and I have a web server here running at this end. Assume that there are two routers through which the data has to go. So, look at what is happening here. So, I am talking about an application layer where the HTTP protocol runs. Let us say this is running, the HTTP protocol runs on top of the TCP protocol, which is a transport layer protocol, which runs on top of IP, which is our network layer protocol, and then this runs on top using an Ethernet interface, let us say. My assumption here is that the Ethernet interface will take care of all these, link plus MAC plus physical. Okay. So, I am having only 4 different protocols that we are looking at here, one at the application, one at the transport, one at the network, and one below it. Okay. So, we have the HTTP protocol, TCP protocol, IP protocol, and then the Ethernet protocol, the Ethernet interface. Okay. So, now let us look at how the data will flow. HTTP message will be taken from here, will be given to TCP, it will pass it on to IP and give it to the Ethernet interface. It will go through this Ethernet interface. The Ethernet interface will remove the additional headers that Ethernet has added and give it as an IP packet over here. So, when it comes to this IP protocol running here, it receives whatever IP packet was sent by this IP layer on this host. Okay. And then this will give it, by looking at its routing table, it will give it to say the next interface through which it has to be sent to the next router. It could be a SONET interface that we have here. Okay. So, through this SONET interface it will come to this router again. When it comes to the IP protocol running at the network layer, again what this sees is the IP packet that was sent from here, which basically is the IP packet which came from this end. Okay. So, which has the information of what is the destination the IP address to which this packet has to be delivered. So, using that information by consulting its routing table, it will again forward that packet to the end machine. So, at the end machine it receives the IP packet which was actually originally sent by this host. Okay. So, by looking at that, by ascertaining that it has come to actual destination, it will remove the IP information and pass it to the TCP layer here. So, what this TCP receives is the TCP segment that was sent by this host, right. So, you can see this is why we say the TCP protocol is a host to host or an end to end protocol. That is, what information is put in by this TCP here is only examined by the TCP protocol running at the other end of the machine. Then this will remove the TCP information and give it to the application, which is the web server, which understands the HTTP protocol. So, it interprets the HTTP message and then gives a response to it, and when it gives a response, again you can see the same thing happening in the reverse direction, flowing through the various routers until it reaches the host at the other end. So, you can kind of see that starting from an application, how the data will actually flow through the various protocols and reach the other end. So, the next thing that we will look at, okay, is in terms of understanding the performance of a network. Now, given that we have these different protocols and different devices through which these messages have to be routed, right, before it reaches the end machine, and given that there is a multiple interaction that takes place between the routers, there are various parameters which can affect the performance of a network. Okay. So, when we start identifying the performance parameters, there are 3 things that we normally look at. So, one is we talk about delay, we talk about bandwidth, we talk about data loss. Okay. These are important parameters which are used to characterize how well a network performs. We will look at each of these in detail, in some amount of detail, okay. But you can intuitively understand why these are important. Delay tells you how much time it will take when the data is transferred. So, too much delay may not be okay in many cases. And we can talk about bandwidth, which talks about the rate at which data is transferred. So, a high rate of data transfer obviously is desirable in many cases. And data loss, obviously we do not want data to be lost, but data would be lost because of some physical disturbances or because of physical phenomena. In those cases, what exactly has to be done? So, that also is something that needs to be considered. Okay. Additional parameters that one would consider may be things like security, mobility and so on. So, all these also affect the performance or the usability of the network as such. Okay. So, it is not just in terms of raw performance, but we also consider usability, because after all, what is a network there for? It is for users to use it. So, users should be able to use it in a comfortable manner. So, we will first take a look at these 3 parameters, that is delay, bandwidth and data loss, okay, and understand what are the components in the network which actually contribute to this delay, bandwidth and data loss. Okay. So, when we talk of bandwidth, okay, the term that we also use is throughput, okay, which stands for the amount of data transmitted per unit time. Okay. And when we talk of throughput, we also distinguish between link throughput and end to end throughput, or link bandwidth and end to end bandwidth. The notation that we normally use is kilobytes per second. You will see that when we use a capital KB, it refers to kilobytes, and a small case b refers to bits per second. So, it could be megabits per second, kilobytes per second. Okay. So, kilobyte per second is about 2 power 10 bytes, megabit per second is about 10 power 6 bits per second. So, this is the order in which we normally talk about bandwidth. Okay. It could be kilobits per second as well, but just to give you an idea. Okay. And we talk of delay, we are talking about the time that is taken to send the message from point A to point B. Okay. Again, we can, there are two ways of looking at the delay. It could be just a one way delay, that is going from one end to the other end, or you can also look at a round trip time delay, what is called as a RTT. Normally we use this term RTT as the round trip time. It is for data to go from one end to the other end, and you normally get an acknowledgement from the other end saying that data has reached. So, in interactive applications, for instance, this round trip time becomes very important. There are some applications where I may not be too much worried about round trip time if I am only worried about how whether the data reaches, that the data just has to reach the other side. I am not worried about getting an acknowledgement. Okay. So, in which case you may just care about one way latency, but otherwise normally we are worried about this round trip time or the two way latency. Now, what are the components which add to this latency? Okay. So, if you look at it a little in detail, you will find that there are three different components which add to the delay or the latency. One is a propagation delay. This is the time that it actually takes for the signal to propagate along the media. So, whatever be the media, we know that if it is light, it will travel at a particular rate of 3 into 10 power 8 meters per second, right. So, similarly for the signal to actually propagate on the media, there is some amount of finite time that it will take. So, that will tell me the propagation time. In addition to that, there is a rate at which I am transmitting data. So, for instance, we talked about data throughput, right. We talked about I could be transmitting data at 2 power 10 bytes per second, or I could be transmitting data at 10 power 6 bits per second. Okay. So, depending on the speed at which I transfer data, obviously the amount of time taken to transfer the data will vary. If I am transmitting at a higher speed, it will go faster. So, I have this one more component called the transmission delay. Now, in addition to these two, there is another delay that comes up, which is called as the queuing delay. Now, this comes especially when you have data going through multiple routers in a network, because there is data coming in from various sources which have to be sent along to various paths. So, they will come and wait at these routers in some queues before they can be serviced and they can be sent along the different paths. So, there will also be something called a queuing delay. Okay. This will depend on the traffic that you have in the network. Okay. So, there are these three components that we have, right. So, propagation delay, transmission delay and queuing delay. So, if you look at propagation delay is easy to measure, right, because it is just the distance by speed. Now, both these are like, all these are at least for a link it can be very easily measured, because we know what the distance of the link is if it is a point to point link, and I know what is the speed at which the particular signal is propagating. So, I can find the propagation time. Similarly, transmission time depends on what is the size of the data that I have, whether it is 1 megabyte or 1 kilobyte or 1 gigabyte, what is the size, divided by the bandwidth, okay, the bandwidth that I have, that I am using for this data transfer. If I am transferring 1 megabyte at 1 megabyte per second, it will take me 1 second to transfer it, right, and so on. Okay. So, you can also calculate the transmission. The queuing delay is something that is not so difficult, it is not so easy to calculate, because it depends on the traffic. So, you can only kind of have an estimate of the queuing delay, and based on that take different actions in the network. Okay. So, this is about delay. Let us do a quick calculation to understand the impact of this of these different delay parameters that we have. Okay. So, let us say for instance, I have an optical link of length 300 kilometers, data size let us say is 1 megabyte, okay. Bandwidth 1 kilobit per second, or let us look at 4 different bandwidths. It could be either 1 kilobit per second or 1 megabit per second or 100 megabit per second or 10 gigabit per second. I am going to consider 4 different bandwidths, so that we can see what happens in each of these cases. Okay. And so now given that these are the 3 parameters that we are looking at, okay, so let us look at what will be the delay. Okay. So, propagation delay. Now, how did we say propagation delay is measured? We said propagation delay is distance by speed. Now, we said it is an optical link. So, obviously, it is speed of light. Okay. So, 3 into 10 power 8 meters per second. So, the propagation delay will be length is 300 kilometers divided by 3 into 10 power 8 meters per second, which comes to about 1 millisecond. Okay. So, propagation delay is 1 millisecond. Now, what about the transmission delay or the transmission time? That we said is size divided by data rate or the bandwidth. So, size is 1 megabyte divided by 1 kilobit per second, okay, in the case of a 1 kilobit per second bandwidth. So, that comes to about 8000 seconds. If it is 1 megabit per second, it will be 8 seconds, if it is 100 megabit per second, 80 milliseconds, 10 gigabit per second, okay, 800 microseconds and so on. So, you can see that depending on the bandwidth that I have, the transmission time will vary, but the propagation delay will remain the same, because it only depends on the length of the link and the and whatever is the media that I have. Okay. So, this is just to give you a quick idea of the calculation. Now, given these two parameters, that is the bandwidth and the latency, there is always some kind of a trade off or some kind of a relation that we have between these two. Okay. So, let us look at the relative importance of these two terms. When is bandwidth more important for me and when is latency more important for me? So, let us say I am transmitting 1 byte. Okay. Now, when I look at 1 byte transmission, if I look at the delay 1 millisecond versus 100 millisecond, or if I look at the data transfer, whether I am able to transfer, my bandwidth is 1 megabit per second or 100 megabit per second. Out of these two, which parameter will dominate? You can see that after all I am transmitting only 1 byte. So, how does it matter whether I am transmitting at 1 megabit per second or 100 megabit per second? Whereas, if I have a link which has a latency of 1 millisecond or a 100 millisecond, that is something which I need to take into account. See, the point I am trying to say is, I have a link which has a 1 millisecond latency, I have another link which has 100 millisecond latency. Out of these two, for a 1 byte transfer, which one will I choose? Obviously, I will choose a 1 millisecond latency, because that really matters for me, right, because 1 millisecond to 100 millisecond for just transferring 1 byte. Whereas, if I were to choose between data rates of 1 megabit per second or 100 megabit per second, after all I need to transmit is 1 byte. So, this data rate would hardly matter when I am transmitting very small amounts of data. But look at this other option that we have here. Okay. So, let us say I am transmitting 25 megabytes of data. Okay. My data size is large. So, here you can see that the data rate is more important here, that is 1 megabit per second versus 100 megabit per second. Obviously, I would choose 100 megabit per second for transmitting a 25 megabyte data, because that will really make a difference in terms of the transmission time. Whereas, the latency that you have, right, that is 1 millisecond versus 100 milliseconds, it really would not matter, because when I am transmitting 25 megabyte of data, already because the data transfer rate itself, there is a time delay that I have, the transmission delay itself is significant. A small delay that I have in terms of whether it is 1 milliseconds or 100 millisecond end to end latency may not really matter. Okay. So, we always have this these two parameters that we need to understand very clearly in terms of which becomes important in which situation. So, we always talk about this trade off that we have between the bandwidth and the latency. So, if I have infinite bandwidth, so let us look at the case where I have infinite bandwidth. What I mean by infinite bandwidth? I can transfer any amount of data, right. So, in those cases you will see that the round trip time, okay, that is very important, that becomes a dominating factor. So, because we said the throughput is the transfer size by the transfer time, okay, and the transfer time is given as your RTT round trip time plus the transfer size divided by bandwidth. The round trip time that we talk about, right, that is the latency that you have from one end for data to be transferred from one end to the other end and back to the source. Okay. So, these two things become very important. So, another term that we talk about when we talk about this delay and bandwidth is also something called the delay bandwidth product, which again is very important in the context of our round trip time and so on. Okay. So, what I mean by this delay bandwidth product is that if you look at a particular line, okay, that you have, that is from one end to the other end or from one end to the other end and back to the other to the transmitting end again. Okay. So, you can look at the whole thing as some kind of a pipe. Okay. So, what we mean when we talk about delay bandwidth product is that we are trying to find out the amount of data that is there in the pipe. Okay. So, what do I mean by this pipe? You can look at this pipe as having a particular capacity, right, diameter, right. So, which is the bandwidth, okay, and so much of data is going to be sent for this much amount of time, which is your delay. So, for instance, if I take a round trip delay of 100 millisecond, okay. So, at a given point of time when I transmit data, for this data to reach the other end, it will take 100 milliseconds. Okay. So, when this data is going along this line, along this pipe till the other end, obviously I am continuing to transmit data over here, right. So, if I look at the end of 100 milliseconds, you will actually find that this data has reached this other end, but meanwhile there is data filling this entire pipe, right. So, we are talking about how much of data is actually filling this pipe or how much of data is in flight in the sense it is still going from one end to the other. Okay. So, data in flight, if I want to calculate, how do I calculate that? I calculate that as the product of the bandwidth that I have, how much data I am sending, right, per second into the time that it takes for the data to reach from one end to the other. So, we talk about something called the delay bandwidth product. So, if I take a delay of 100 milliseconds and the bandwidth is 45 megabit per second, okay, so altogether 45 megabits per second, right. So, it will take about 560 kilobytes. So, 560 kilobytes of data will be the data that is in transit or in flight. Now, why do I need to worry about something like delay bandwidth product? So, you will find that when I am transmitting data at any point of time, okay, there are 560 kilobytes of data which is in transit. So, if there is something that happens in the network and the data is lost, it is not just one byte or one unit of data that is lost, but it could be a whole lot of 560 kilobytes of data that is lost. Okay. So, similarly, whenever we are dealing with large networks and we talk about these kind of round trip time factors and so on, this combination of delay and bandwidth is often useful to understand the actual performance of the network. So, as we look at other details in various models which come later in as a part of this course, you will see how this delay bandwidth product becomes a very important factor. But right now we need to understand this, that multiplying the delay and the bandwidth gives me a very useful information about the network, which tells me how much of data is currently in flight or currently in the pipe. Okay. So, this is something we need to understand. So, the third parameter that we talked about was packet loss. Okay. So, when we talk of packet loss, this again has a direct relation to applications, because there are certain applications which are tolerant to losses, whereas there are certain applications which are not tolerant to losses. In fact, normally we talk about these two classes of applications. We talk about delay tolerant applications and we talk about loss tolerant applications. So, we say delay tolerant application versus loss tolerant applications. What do we mean by this? What we are actually trying to say is, if you take a delay tolerant application, this is an application where it really does not matter if it takes a little more time for that data to be transmitted, but it cannot tolerate any losses, data cannot be lost. If I take a loss tolerant application, this is talking about applications where I can tolerate losses. If occasionally one byte is lost, one frame is lost, okay, little amount of data is lost, it can still be tolerated. I can still work with that application can still work, but it may not be tolerant to delays. That is, if there is a delay, then my entire application starts failing. Okay. So, we talk about these two classes, delay tolerant applications versus loss tolerant applications. Example of a delay tolerant application would be file transfer. So, in file transfer, obviously when you transfer a file, you do not want data to be lost. Let us say you are doing some kind of bank transfer, okay, amount you are transferring, you are doing an e-transaction. Obviously, that has to be it cannot afford to take any losses. Okay. So, it is not, it cannot take losses, but if it takes a little while, okay, you may, if it takes instead of 1 millisecond, if it takes 10 milliseconds, that may be fine, you may be able to tolerate that kind of a delay. But on the other hand, if you are looking at an application like movie streaming, you are downloading a movie or doing a streaming of a video or a movie and you are watching it. Now, if there are delays, okay, if you receive one frame and you do not receive another frame and or it comes after a very long time, then what happens? Your movie viewing experience itself becomes very unpleasant, right, you are not able to view it correctly. Okay. So, here I cannot tolerate delays, but you may be able to tolerate losses. How is this possible? Because you will see that when actually movies are streamed, there are multiple frames that are present, and even if you lose information in one frame, it really may not matter. You may be able to compensate for it by other means as part of the video application itself. Okay. So, in these cases you may be able to tolerate losses, but you will not be able to tolerate delays. Okay. So, we need mechanisms to detect errors or to correct errors, or by repeating transmission you should be able to take care of the error. So, this is something that we have to always worry about. And of course, we need mechanisms that will help us to tolerate delays. So, we said that when it becomes a loss tolerant application, it also you have to remember that you need to have some kind of a mechanism that will allow you to tolerate delays. So, with these parameters, we normally talk about something called a quality of service. This is another very commonly used term when we talk about a network service. So, quality of service typically defined by these parameters, these three things that we looked at: delay, bandwidth and loss. Okay. So, and when we say that we want to use a network, we say that the network should be able to provide some kind of a guaranteed quality of service. So, this kind of the design of these kind of networks is what we will be studying in terms of this course. That is, how do I design networks which are able to provide guaranteed quality of service? How do applications interact with these kind of networks? Okay. What happens when the quality of service is not that was guaranteed by the network is really not provided. Okay. So, what are the various options that we have when you have to design these kind of networks? You will see that as we are going more and more towards many multimedia kind of applications that we are using today with lot of videos and other things that are becoming very popular among the users, quality of service is becoming a very important factor. So, designing of networks is no longer just connecting up different machines and making sure that data goes from one end to the other, but we also have to make sure that quality of service is provided. So, to summarize what we have looked at in this module is that we have looked at the functions of each layer, why each layer is added, okay, and we looked at it from the perspective view, from the perspective of an application, of how applications can be, how applications require these different functionalities. We looked at these performance parameters which are delay, bandwidth and loss, and we looked at how you can estimate those parameters or calculate those parameters. Okay. So, this is what we have looked at in this particular lecture.